Your chapter 6 homework has already been submitted, but we need to go back and talk about air drag. That's an important topic from chapter 6 that's going to show up in the future. Anybody who's ever been a passenger in a car or a driver in a car and stuck their hand out the window at high speeds knows about air drag. It becomes significant as your speed increases. That's why you see a dog's ears flapping in the wind when the dog pokes its head out of a car window. In fact, air drag can be so significant that it can equal your weight or even exceed your weight if you're a skydiver. I take that back. If it were to exceed your weight, that would have to mean that you were launched out of the plane at a speed greater than terminal speed. And that sounds really dangerous. So uh, let's look at that. This was supposed to be a person falling through the air. It started out okay. I've got two legs here. Now the neck's getting longer. That was not intentional. By the time we get to the last picture, to me, this looks like some kind of dog or rodent. So just pretend it's a person in free fall. It's a skydiver. And when you first jump out the plane, sure, you're moving sideways because the plane was moving sideways, but you have not yet acquired any velocity vertically. So at the instant you've jumped out, your velocity is still zero. And that means there's no air drag to speak of on your body. If you're not moving, there shouldn't be any air drag. There's still gravity though. And so if we were to plug all the forces into F equals ma, the net force points down, hence the acceleration points down. And you all know that if the only force is gravity, this acceleration would be 9.8 meters per second per second. Of course, if you're jumping from an airplane that's real high in the atmosphere, I suppose it might be a little bit less than 9.80 because gravity gets weaker as you move away from the surface. Okay, after you've been falling for a few seconds, you've acquired some velocity. And I've drawn a short arrow for the velocity to represent a modest speed. And now when you look at the sum of the forces vertically, you've still got gravity pulling down, but there's a little push in the upwards direction. When you sum these two up, you get an arrow that's shorter than just the gravitational force. And as a result, your acceleration will be reduced in magnitude. So I drew an acceleration vector that still points down, but is shorter than it was before. What's the rule again? If the A vector and the V vector point in the same direction, you're speeding up. So this person is still speeding up, but at a lower rate. The rate at which they are speeding up is less than it was before. It is no longer 9.8, it's something less than 9.8. Seconds later, they're going even faster. Their speed is increased to a greater value. That's why the velocity vector is greater in magnitude. It's longer than the previous velocity vector. And as a result, the drag force is also greater in magnitude. So I made this drag vector longer than this drag vector. At this point, I'm not using numbers. I'm being purely qualitative, but in a moment, we will look at how to calculate actual numbers for the drag force. Notice that I've made the acceleration vector even shorter. If you were to sum these two forces up, you would get a net force that still points down because gravity is still longer than drag, but it's a much shorter vector now. And if the total force is reduced in magnitude, so too will be the resulting acceleration. Finally, this skydiver has reached a speed great enough that the drag force is equal in magnitude to the gravitational force. And when you get to that point, when the air is pushing up on you just as hard as gravity is pulling down, the net force on you would be zero. What happens to your acceleration when the net force on your body is zero? Your acceleration goes to zero. So you could say that at this point, the acceleration terminates. There is no more acceleration. And that is why they call this particular speed the terminal speed. At terminal speed, the drag force up on your body is equal in magnitude to your weight, which means it's a pretty large force. If you weigh 200 pounds with all your skydiving gear, the air is actually pushing up on you with 200 pounds of force. 200 down, 200 up, there's a net force on you of zero. So terminal speed, that is not the speed at which you terminate. That would be the speed you're going when you hit the ground. But we're talking about the speed at which you stop accelerating. So assuming you're in free fall, I shouldn't really say free fall because I'm reserving the term free fall for a situation in which the only force on your body is gravity. In this case, there's a second force, drag. So if the only two forces on your body are air drag and gravity, then the definition of terminal speed would be the speed at which the air drag force equals the gravitational force. That's supposed to be a capital letter D. And now we're left with the question, how fast is that exactly? We know that as speed goes up, air drag also goes up. But what is the exact dependence? Is it linear? Is it quadratic? Is it exponential, logarithmic? So I could write drag as a function of speed is question mark. How exactly does it depend on the speed? Let me just draw some sample graphs. We can ask which of these is the most reasonable. Suppose it's a simple linear dependence, drag versus speed. This would suggest that, let's see here. Suppose you're going down the street in a vehicle at 40, well, not the street, let's go with the highway, 40 miles per hour. You experienced a certain amount of air drag. Just imagine sticking your hand out the window and feeling the drag on your hand. Then your car accelerates up to 80 miles per hour on the highway. Do you only feel twice the amount of air drag on your hand? If this proportional relationship were accurate, that would suggest that going from 40 to 80 miles per hour would double the drag force on your hand. But when I imagine myself in a car, if I stick my hand out of the driver's side window at 40 miles an hour, I don't really feel a whole lot of air drag. There's some, but it's not significant. At 80 miles an hour, it's very significant. I would have to guess that the air drag on a dog's ears with its head out the window at 80 miles an hour is quite a bit more than double the air drag at 40 miles an hour. So I don't think this is accurate. I could also imagine something exponential like this, where it suddenly takes off real quickly. That makes a little more sense because you don't feel a whole lot of drag, between 0, 30 miles per hour. And then by the time you get up to 70, 80, 90, there's quite a bit. However, there's something unrealistic about this even because as you go from, let's say, 80 miles per hour to 90 miles per hour, there would be a real sharp increase in drag. And that doesn't seem realistic either. There's a lot of drag at 80 miles an hour. There's a lot of drag at 90, but the difference isn't this severe. Of course, one of the silliest functions at all would be this one, which suggests that drag doesn't change as you go faster or slower. We know that's bogus. It turns out that for things like skydivers falling through the atmosphere or baseballs moving through the air above a baseball stadium, what else? Birds flying through the air. It turns out that a very accurate model for drag versus speed is simply a quadratic one, where drag depends on the square of the speed. So we can say that the drag is proportional to speed squared. Drag proportional to speed squared. And that means that if you drive twice as fast, well, 2 squared is 4, twice the speed would imply 4 times the drag force. And that kind of seems consistent with experience because if you drive 30 miles an hour, you can feel some drag on your hand when you put it out the window, not much. If you go from 30 to 60 miles per hour, you've doubled your speed, you would expect 4 times the air drag. And that sounds about right because it's definitely much more than double, but it's not something crazy like 100 times the drag force. Now let's just suppose for a moment that the actual drag force versus speed had a more complicated dependence. Maybe it does something like this. It sort of scoops up like a parabola, then levels out, and then does something even wilder. How would you even determine this curve to begin with? Well, you could study it in a lab. You could set up an experiment. Let me go to share screen here. I just pulled up an image on Google. Here's a tennis ball in a wind tunnel, and they're blasting it from the side with a fan. And they must have put some sort of dye or smoke into the air so that you can visualize the streamlines. we're not interested in the streamlines here or the turbulence back here. I just want you to imagine that maybe this tennis ball is suspended from a string inside a wind tunnel, and you can turn this fan up higher and higher. In other words, you can control the speed of the air within the wind tunnel. Now, whether the tennis ball is actually moving to the left through the air or the air is moving to the right over the tennis ball, it's irrelevant because motion, in a sense, is relative. So if the wind is blowing past the tennis ball at 20 miles per hour, that's the same as the tennis ball flying through the air at 20 miles per hour. And that means that you can make some data points here and plot them. Suppose, this is not in the picture, but suppose there was very sensitive force probe right here. Think of like a spring right here attached to a computer sensor or a sensor that's interfacing with the computer. And we know that as this air flows past the tennis ball, it's going to push on the ball. Imagine a push to the right. There has to be an equal and opposite force to the left in order to keep this ball where it is. So the harder the wind pushes, the harder the force probe would push back. And that means that you could record the wind force as a function of speed. For each different wind speed, you could record how hard the force probe would have to push back to keep the ball in equilibrium. And that number would be the same as the drag force. Let's see here. I'm trying to switch tabs and this garbage is in the way. Okay. So maybe this curve was produced because you had taken a bunch of data points in your wind tunnel. You kept turning up the speed and recording the resulting drag force, and then you ask a computer to fit a smooth curve through all these data points. Well, you don't actually get something funky looking like this. What you get is something that looks a lot more like this, at least for reasonable speeds. Once you get towards the speed of sound and certainly beyond, I'm imagining it's quite a bit more complicated than just a quadratic dependence. That's a rather challenging branch of physics, actually. Fluid dynamics, there's a lot of vector calculus in that subject, and it's probably not something you'll have to encounter. I take that back. If you're going to major in aerospace, you'll certainly see some of that stuff. But it's not a subject that I studied much in my education. Okay, well, I want to talk briefly about Taylor series. Even if the drag force did have this bizarre shape, I'm sure you know of no one function that looks like this. You know of x squared, e to the x, cosine of x. You're familiar with all those shapes, those curves, but you can't think, I'm guessing you can't think of a single function that has this shape. Nonetheless, you can build this function up out of simpler functions. That's called the Taylor series. Let me go back to browser here. But this window's in the way, so how do I move this out of the way? Okay, I'm gonna have to pause for a moment. Okay, let's take a look at an example of a Taylor series. I have to hit the share button again. You should have encountered these in your second semester calculus class, I believe. And they're usually presented kind of briefly in the calculus classes because there's so many other things you need to cover. But Taylor series are really useful in physical sciences. Take a look at this, let's see here, cosine function. It's the blue curve here. Well, we already know that the cosine function, it's got a name, we know what the shape looks like. You may have looked at the power series expansion of the cosine function. Cosine of x can be written as 1 minus 1/2 x squared plus 1 over 4 factorial x to the 4th, etc. And graphically, what that means is, well, let's start with the very first term. I said cosine of x is equal to 1 minus x squared over 2 factorial plus, etc. That first term, 1, that's a horizontal line with a height of 1. And you'll notice that the blue cosine curve in the vicinity of this point is actually really close to that orange line. So for values of x really close to 0, the cosine of x is practically equal to just 1, as long as x is a really small number. As soon as you move off to the right, though, this orange line does not at all approximate this blue curve. However, this green parabola does a pretty good job of approximating the blue cosine curve in a larger range of values of x. So if you add a particular parabola to this orange line, you will get this green parabola. And the green parabola does a pretty good job of approximating cosine of x. So as I mentioned, the first two terms in the power series approximation are 1 minus x squared over 2. 1 minus x squared over 2 is this green parabola. The more terms you add, the higher powers of x as you insert those into your Taylor series, the better your Taylor series approximates the original function. In this case, it's cosine of x. And it works not just for cosine and sine, but a whole range of functions. There's just a few restrictions on the function if you're going to use a Taylor series. Something about differentiability, and the second derivative has to be continuous. I forget what the conditions are. We don't care about that. The idea is, and let me go back to the notes here. The idea is whatever this experimental curve is that you determined in the wind tunnel, you could build that up out of powers of v as a Taylor series. So the drag as a function of speed would be some constant plus some other coefficient times v to the first power, plus another coefficient times v squared, plus another coefficient times v cubed, plus etc. And you just continue on to higher and higher powers of v. And all you have to do is choose these numbers. These are numbers. Choose these coefficients correctly, and you can get the sum of all these terms to match this curve really well. That's called a Taylor series. And you may have heard that these coefficients have something to do with the derivatives of this function. In any case, you could determine these experimentally. So if you take all this data from the wind tunnel and ask a computer to find the coefficients here, which produce a function that best approximates this, what you find is, as long as you're talking about things like skydivers, baseballs, birds, rocks falling through the air, as long as you're talking about ordinary objects traveling at ordinary speeds, I'm talking about less than the speed of sound, it turns out that this number is irrelevant, this number is irrelevant, and all these higher numbers are so small that they contribute practically nothing to how drag depends on speed. And all we're left, oh, I goofed. This is the one that's irrelevant. This is the one we want. This turns out to be the dominant term, the quadratic term, as you may have guessed from the previous, or the notes just a moment ago. So what remains to be seen is what exactly is this coefficient. We know that as speed increases, drag increases, but what's the constant of proportionality out front? We know that drag is proportional to v squared, but what is that constant of proportionality? And you might imagine that it's going to depend on a number of things. If you drop a baseball, not a baseball, a bowling ball. Bowling balls are pretty heavy. They're spherical. If you drop that versus, imagine a flat board of whatever material the bowling ball is made out of. What is a bowling ball made out of? I have no idea. But take that same material, and let's say this is a 12-pound bowling ball. Take 12 pounds of that same material and form it into this shape and drop these two. Which one's going to be falling the fastest after 10 seconds? If you dropped them both from the top of a mountain, I'm pretty sure that after 10 seconds, this one's going to be falling faster because you have some sense that it's more aerodynamic than this one. In other words, this one should experience more drag. So even if they were both falling at the same speed, let's say that at some particular moment they're both falling at 30 miles an hour, I would expect this one to still be speeding up more quickly. This one's going to experience more drag. So the shape of the object, the shape and perhaps even the lateral dimensions are going to have something to do with the value of this coefficient. This coefficient will depend on a number of things. And I'll just give it to you. It's in your book. Your book does not derive this coefficient. They don't use mechanics to show where this number comes from. If you want to see that, you'd have to get a more advanced book, like a junior or senior level mechanics book for physics majors, or I'm certain that a lot of textbooks on aerospace engineering would probably cover this, but here it is. The drag force as a function of speed. Here's how I remember it. I say half Poc, as in Tupac, but with a half instead of a 2. There it is. Half Poc times v squared. You still have your v squared dependence, but that coefficient that I was referring to, here I called it A2. You can dump the A2 now. We're not going to use that. All of this stuff is A2. There's a number of factors that determine the coefficient in front of v squared. The 1/2, well, that's, again, if you want to see where that 1/2 comes from, get a more advanced book. I've probably seen it at some point, and I've totally forgotten where it comes from, but this is the Greek letter rho. It looks like a P, that's why I'm saying half Poc, but it's really the Greek letter rho, and it stands for air density. Air density. Of course, as you go, let's say, higher in the atmosphere, where the air density drops, you would expect to experience less air drag. When a little chunk of rock from outer space zips into Earth's atmosphere at extraordinary speeds, when it's real high in the atmosphere, there's not a whole lot of air drag. But as it gets deeper into the atmosphere, the air density increases, and this drag force becomes enormous, and there's enough thermal energy dissipated by drag force to make that little rock burn up and glow very brightly, and that's what we call a meteor. So of course the drag is going to have something to do with air density. I mean, if the air density was 0, if there were no air to speak of, there would be no drag, right? So it makes sense that there's a rho here, because if rho was 0, the drag force would also be 0. This capital A, this is the cross-sectional area presented to the oncoming wind. For instance, if you drop a can of refried beans straight down through the air, or a can of tomato sauce, if this thing is falling downwards, if you're the air, that's a silly thing to say, but if you're the air, you could just imagine that, am I saying this right? No. If you're the can of beans, imagine you are the can of beans, you would see the air rushing at you this way. And the cross-sectional area of the air would be this. Yeah, you think of it this way. It's really just the area that is perpendicular to the velocity. So the velocity is this way. You're looking at the area that's perpendicular. So we're not interested in the lateral surface area. Like if you took the label off that can of beans and measured the surface area of that, we don't care about that. It's the area that's perpendicular to the velocity. That's the A that goes in there. And now you can already see somewhat how a skydiver could slow themselves down. You could do a pencil dive. Imagine this is your head and your feet, and your arms are folded at your side. If you're doing a pencil dive straight down, or maybe your feet would be at the bottom, the cross-sectional area, if the wind is coming at you this way, the cross-sectional area that you present to the onrushing air is rather small. But if you splayed out with your arms and legs straight out, do an eagle dive, swan dive, whatever they call it, you could present more surface area to the air, and that would increase the drag force on your body. You could slow yourself down that way. So shape has something to do with it, or just overall size has a lot to do with drag force. Just a moment ago, I said shape has something to do with drag force. That's really what this capital C is about, not lowercase c for speed of light. This is a capital C. It's often just called the drag coefficient. And that really does depend on shape. I tried to pull up the graphic from your book with several examples, and it was not available in the instructor's resources. So let me grab the book and we'll just look at it on the page of the book.